In the last lecture, we studied the steepest descent method, which is at one end of the spectrum of optimization methods. And in this lecture, we will study the other method at the other extreme of the optimization methods, and that is Newton's method. These two are developed based on simple, straightforward ideas. Steepest descent method on the straightforward geometric idea, Newton's method based on the straightforward analytical idea. And the straightforward analytical idea of Newton's method is just Taylor series. Okay. So Newton's method, as in single variable problem also, tries to solve the first order optimality condition. And pure Newton's method, therefore, cannot distinguish between the minimum point and other stationary points. You keep in mind this. Okay. So, as I said, we start with Taylor series. So the second order truncated Taylor series of fx around the current iterate xk. That is, for x equal to xk plus delta x will look like this, right? So there is a function value, there is a gradient into delta x plus Hessian of the function at xk, and here we have the delta x terms, 2 degrees of them, right? So this is the second order truncated Taylor series. Now we want to solve grad f equal to 0. That is the first order necessary condition. So for that we need to differentiate this. As we differentiate this, or rather than differentiating it, we could have directly written the first order truncated Taylor series of the grad f itself. It would be equivalent. Anyway, now as we differentiate this is a number, so it produces nothing. This is again a vector, constant vector. This has element of x because delta x is x minus xk. Its derivative is, something. So basically it stands for 1. Okay. The derivative of this would stand for 1. And therefore this appears here. The derivative of this will get hf into delta x. That is this. So this is grad f. And we are out to solve grad f equal to 0. So as you equate this to 0, you can solve for delta x. That is minus grad f pre-multiplied with Hessian inverse. Okay. So that delta x you add to the xk. So you get xk minus Hessian inverse grad f. Now, in actual computation purposes, you do not really invert the matrix because that is too much of computational cost. Rather, you solve this equal to minus grad f, and whatever is the solution delta x that you add, that will be much less computation compared to unnecessarily inverting the matrix, which you don't need. Okay. Now, what is the cost? Cost is, these calculations have very little cost. The major cost is the evaluation of the function, gradient, and the Hessian. And Hessian computation means a lot. So if you count, then at the least, these many equivalent function evaluations will be needed. Okay. I mean, at the least, because this is what you get if you use forward differencing for the derivatives. Central difference would require even more. So it's quite costly, and the cost part is the Hessian computation. Now, costly is worth it because one iteration may produce a lot of advantage, and that is what we will see. Local convergence, that is, the speed of convergence is high, and to show that, or to establish that, to verify that, let x star be a minimum point of a function, with Hessian this HF x star at that point, and that is positive definite because it is a minimum point. Now, by continuity, you know that it will be positive definite in a small neighborhood, and we will talk about that small neighborhood. Okay, so that small neighborhood is suppose this within an epsilon neighborhood. Now, if it is positive definite, then its eigenvalues are positive, finite numbers. The inverse also will have its eigenvalues as positive, finite numbers. The largest of that is largest of the eigenvalues of the inverse, which is the reciprocal of the smallest of the eigenvalues of the original matrix. That is finite, so less than some number sigma, let us say. And the second order error around a point within this neighborhood where things are nice and smooth and everything is cool. Okay, so that also has its Taylor series. Okay, so if you talk about the Taylor series of this, then you will find grad f at x plus Hessian times Hessian at x times delta x plus second order terms. Okay, and so second order terms will dominate. So you can say that the difference of this thing with the first two terms will be some constant into second order, second degree, 2 degree square of delta x. Okay. In particular, this will be true for this delta x also, x star minus x. Okay. So if you put x star minus x in place of delta x here, then we will get x plus x star minus x. So x and minus x go off, fx star, grad f at x star, minus grad f x minus h of x into x star minus x, right, is equal to c times this square, not equal to, less than equal to. Now, we organize this a little bit. Okay. From Newton's iteration formula for xk in this little neighborhood, we want to evaluate this. Now, what is xk plus 1 from Newton's formula? Xk minus this. Okay, we put that, and x star we retain. Now, here, what in the next step has been done is that this hfxk inverse has been taken out, and everything else, whatever remains, is put inside this bracket together. Now, here hf inverse was there, so minus grad fxk comes as usual. 0 I have put from my own hand. Okay, doesn't matter. Now, in this term, xk minus x star, with this was not there, but we are forcibly taking it out. So inside we will keep hf xk, not its inverse. So that will mean the same thing, compensation. Okay, so if you open out this product, this into this will cancel out, and you will get, and see again this minus sign has been put because here it was xk minus x star, here it has been put as x star minus xk, so that's minus sign. Now this 0 that we have put from our own hand freely, that 0 now we will replace with this gradient because that is 0. Okay, gradient at the minimum point, and the rest of it has been posted as it is, except that here it was this matrix times this vector. Okay, and here it is, and the norm of that, and from Cauchy-Schwarz inequality you know that norm of A into B is less than equal to norm of A into norm of B. Okay. So this thing is less than equal to norm of this into norm of the vector. And norm of this is bounded by sigma, and norm of this is bounded by this c delta x whole square. Okay, c delta x mod square. So see this change square. And now take this and divide on the other side, and you get xk plus 1 minus x star norm divided by xk minus x star norm square is less than equal to sigma into c. This is finite, this is also finite. And so this you get finite with the power 2 here. And that shows that Newton's method has quadratic convergence. Okay, this is local convergence. Now let us try to answer the question about global convergence. So this Newton step, is it a descent step? That is, compared to the point xk, is the function value less at xk plus 1? Answer is not necessarily. Okay? See a counter example. Say fx is this. You take the gradient, just faithfully differentiate 4x1 cube 0 minus 6x2 6x1 plus 2x2 plus 0 minus 10. Okay, then with respect to x2 you differentiate and fill this. Now differentiate this with respect to x1, you get this. Differentiate this with respect to x2, you get this, which will be same here, because then you will differentiate this with respect to x1 and differentiate this with respect to x2, you get this. So this is a Hessian. Say we have xk equal to 0. Xk is the origin, where the function value is 0, gradient is minus 10, 0, Hessian is minus 6, 2, 2, 4. Fine. Now see where the Newton step takes us. Xk plus 1, you properly evaluate the step and you get this. And then at that point, you evaluate the function and you get 11.568. Okay. And that is certainly more than 0 if xk was 0. So it's not a descent step. From xk plus 1 has turned out to be a worse point, okay, with higher function value. So it's not a descent step. And that means that Newton's method does not guarantee global convergence. In particular, it does not guarantee that the next iterate will be any better than the present. It can be worse. Now you say, okay, but is the direction good? You remember in simplex method, we sometimes found that some direction is good. Some direction is good, even though the point may not be good. So in that case, we did not go full step, we truncated. So try something of that sort here. And in that case, we can do line search. So is this a line? Is this a decent direction? That is taken as a direction, this delta x vector, is it a good direction to proceed? Even that is not guaranteed. In this example, dk turns out to be this basically, because xk was 0 in this case. So whatever was xk plus 1, that was basically delta x. And that is now taken as the direction dk. Dk is this. And with dk, if you take the inner product of the gradient, which is this, then you see minus 10 by 7 into 10 by 7, that is 100 by, it should be 100 by 49, not 100 by 7. Okay, 100 by 49 into, no, 100 by 7, it is 10 minus 10 here. Gradient is minus 10. Okay, so this is fine. So minus 10 into minus 10 by 7, so 100 by 7, positive. In plus 5 by 7 into 0, that is 0. So you see, the component of the direction along the gradient is positive. So the direction is not a descent direction, it is an ascent direction. So in this direction, not only the full Newton step is a step taking you above, in that direction, even infinitesimal distance will take you higher in the function value. And so you cannot trust it either way. Okay. So even line search will not give you anything. Now you ask this question in a different manner. You ask under what condition this would be a descent direction, and that you can answer. Newton's step as a search direction. So now we are asking under what condition Newton's step can be a descent direction, taken as a direction at least. And that for that we can give the answer very easily. Dk transpose grad f should be negative. That means dk transpose this thing should be negative. And that means minus dk transpose. Okay, so sorry, dk transpose grad f. So this transpose grad f. So this transpose will mean grad f transpose inverse transpose negative. Okay. So inverse transpose will be inverse only because it's symmetric and its inverse is also symmetric. So you get this. This is negative. And under what condition this would be guaranteed? Now you say that if the Hessian is positive definite, then its inverse is also positive definite. Then any vector transpose that matrix into vector will be positive. Okay, except for 0, so which is not the issue. And then this negative sign will ensure that this whole thing is negative. So the negativity of this thing is guaranteed if the Hessian is positive definite. So this is the little result that we have got. If we are operating in a neighborhood where the Hessian is positive definite, where the function is convex, then the Newton step will give a descent direction at least, even if the full Newton step is not a descent step. And you see in the previous example, at origin, this was 0, this was 0. So minus 6, 2, 2, 4. It was certainly not a positive definite matrix. Okay? And that is why we could not expect the Newton step to be a descent step or a descent direction. Now, as I told you, it is possible sometimes that the Hessian is positive definite, and so Newton iteration gives a descent direction, even if the full Newton step is not a descent step. For example, see this. Here is the minimum point and these are the contours. If this is xk, Newton step might suggest you to come here, which is quite a big jump. Now, along this direction, if you go slowly, then you see you are cutting contours inward, 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 where finally you will touch a contour here, which is the minimum point, and then cut the same old contours back again, outward, 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 and on the way cut even the contour which is passing through this original point. Okay, so whatever was the function value here is the same as here, and you would cut that also outward and end up increasing the function value. Okay, so it is possible that it not only overshoots the minimum point but overshoots so much that is it goes beyond the contour curve or the level surface through the original point from where the line started. So Newton full step might give you such a big jump. But the remedy of that is easy. You say that we take Newton's step as d, the search direction, and then say that we will conduct a line search with this. Okay. Alpha equal to 1 means full Newton step. Alpha equal to 0 is where we are. In between, whatever is the minimum point, we will take that. So that is the line search we conduct. In this case, line search has not only a lower bound but an upper bound also. Okay, which is unusual, not in every case. So this line search is one aspect of what we next study, that is modified Newton's method. Newton's method as it is unreliable because it does not have global convergence. So we have to modify it, and this will be one modification. There is another modification to ensure that the Hessian is positive definite. That's not very difficult. So the two modifications to Newton's method, one is replace the Hessian by adding a positive number gamma to the diagonal entries. So by that, you would increase all the eigenvalues by gamma. Okay. So whatever was the negative eigenvalue compared to its magnitude, if gamma is higher, then you would end up pulling all the eigenvalues on the positive side, and that will be good enough. Okay. But how do you know what gamma would suffice? Okay. If you put a very large one, then it will turn out to be useless. Okay, because it will look like a scalar multiple of identity itself. Hessian will become inconsequential. Okay, so that is the problem. We are coming to that. And the second modification is what we have already discussed, that we will replace the full Newton step by line search. And for that, we will not bother to determine. We will just do it as a matter of course. We will not bother to determine the need, because if there is no need, then the line search will immediately conclude very easily. Okay. So the first step of diagonal enrichment by addition of a positive number gamma to the diagonal elements is to increase eigenvalues by gamma, as we discussed. Now, how does that get accomplished? If the most negative eigenvalue is lambda n, then its magnitude plus an epsilon, if you take as gamma, then that will be rescued. And with that, all the other eigenvalues, which might be negative of lesser magnitude, will also be rescued. Will be rescued with a bigger margin. This is here epsilon, you basically have to select which is an acceptable small number, which you are ready to accept as an eigenvalue. Very small positive numbers also you would not like, because that will cause severe ill conditioning. Okay. Now, if the lowest eigenvalue of the Hessian is already above epsilon, then you don't do anything. Then that Hessian would be used unchanged, and in that case, you would get full second order, quadratic convergence. Okay. Now, here is the catch. Matrix eigenvalue problem is a costly computational process. So how will you determine this? You can determine. Now, one relatively efficient method to detect if HF has any negative eigenvalue, and in that case, to determine it, is by power method. Because power method gives you the largest magnitude eigenvalue. Okay. So first time when you do that, in our case, it is unlikely to be negative. Okay. Because I mean, the largest magnitude eigenvalue of a Hessian matrix being negative is a little too much. Okay. So typically it would be positive. Fine. Now what you do? You first round subtract that maximum magnitude eigenvalue from all the diagonal entries. So you will shift all the eigenvalues leftward, that is forcing them to be negative. So earlier, whichever was smallest, whether positive or negative, now will get pushed to the extreme left. And in the second round, when you apply power method once more on this modified matrix, then that would end up as the largest magnitude eigenvalue. And then to that, you add that old largest magnitude eigenvalue which you had, and then you would precisely locate it, and you can see whether it is on that side of zero or this side of zero. So from there, you would get this worst negative eigenvalue, if any. Okay. If there is, then that fellow's magnitude plus epsilon you will add as gamma. If there is none, then you will not bother. So this is the plan. Okay, so modified Newton's method can work, and so we produce here a little listing of the algorithm which you can use to implement it in a program straight away. So select the starting point and tolerance values on function improvement, gradient norm, okay, and then start the iterations. Iterations will be what? Evaluate grad. If the grad is extremely small in magnitude, then stop convergence. There is a normal convergence. Else evaluate the Hessian. Choose gamma by whatever method you can do that best. Develop the replacement Hessian if needed. Then solve that replacement Hessian into dk equal to minus grad, negative grad. So from here, by solution, you get dk. Conduct the line search along dk from 0 to 1. Okay. And according to the result, update the point, evaluate the function at the new point, and see if the function change is significant. If it is insignificant, then stop. That is a subsidiary termination condition. Otherwise, go to the next iteration. Okay. Of course, here there will be another little step. I mean, that is trivial. That is increment k and go here. Okay. So increment k and go to the step 2. So global convergence is thus engineered in Newton's method. One, by enriching the diagonal of the Hessian, and two, by line search. Okay. Now, at what cost we have accomplished this? First of all, to begin with, anything to do with Newton would mean Hessian. Okay. So modified Newton also has Hessian, and its evaluation is costly. Gradient is not too much of cost. Okay. Hessian evaluation means too many functions have to be evaluated. Okay. Selection of gamma requires something to do with eigenvalue problem, which is also typically is a costly problem. Power method is relatively cheaper compared to general eigenvalue problem methods, and that is fine here because we don't need all the eigenvalues. We need only the worst. Okay. And but still, for a matrix of large size, that would be something, a distraction. Okay. Line search is there as another computational cost, and this was something genuine, which is sort of expected. And in Cauchy's method, this was the only major cost. In steepest descent, this was the only major cost. Nothing else was there. Okay. Solution of a linear system for decay, that is this. This is not much. Okay. So this is not much. This is considerable, but sort of needed in many of the methods. Okay. This is something out of the way, which may be costly for large matrices. This is one big issue. Okay. So keep these issues in mind. But now with this, whatever be the cost, you have got a good working method which you can utilize. But cost is high. You have to keep in mind that. And now global convergence has been engineered, as we discussed. Local convergence is already excellent, but that excellent local convergence property would be really expressed in modified Newton's method only in later iterations when the Hessian would be actually positive definite on its own and completely and truly utilized. Okay. In earlier iterations, it might have been engineered and so might have lost some of its natural high power. Okay. So, points to note from this lecture. Based on Taylor series and using both gradient and Hessian, a Newton's method iteration attempts to find a stationary point. Okay. Satisfy first order optimality condition. It exhibits a quadratic local convergence, which is the best that is ever hoped for, but has absolutely no guarantee of a global convergence in the general setup, limiting its direct utility severely. However, if the function is known to be convex, then you don't have to do anything. Then Newton's method can be used as it is. If the function is known to be convex, that is, Hessian is positive definite everywhere, then you can just use it without looking left or right. Modified Newton's method salvages Newton's method for general problems by diagonal enrichment of computed Hessian and a line search in place of a Newton step. Now, computational cost per iteration remains the issue, which we will address in later methods. And make note at this point that till now we have studied two methods successively: steepest descent method and Newton's method. The first one, very good at global convergence, poor at local convergence. The second one, very good at local convergence, poor at global convergence. Okay, so the two operate at the two extreme ends of the spectrum of optimization methods. And in the next lecture, we consider a hybrid method which will try to get the benefit of both the worlds. Okay, thank you.